Hey everyone, in this video we're just going to recap all the basics of factoring. So that's your GCF, your dots, and your trinomial method, all that you covered in Algebra 1. So let's get started here. Remember, to factor, it's just to rewrite an algebraic expression as an equivalent product. So that being said, we're going to start with the greatest common factor. So when I start with the greatest common factor here, we're looking for whatever term that can be divided into both nicely. Now, greatest common factor can involve numbers or letters. So when I first look at this, I'm going to think, hey, what number can I divide both of those two by? So one of those, the greatest common factor they have in common, is a 2. The other thing that I'm going to ask is there a letter that they both have in common that we can divide out? And for us, that's going to be an X. Now, the greatest common factor itself is the 2x. That's what they both have in common. But if I write it as a factored expression, that piece goes in front. The GCF comes in front, and then it's like I divide both of those terms by a 2x. So 6 divided by 2 is 3. X squared divided by x is x. 10 divided by 2 is 5. And x divided by x is 1, which I can just leave here because 5 times 1 is 5. And that is the idea of what I'm going to do. So I'm going to keep with that process. On number 2, I looked at they all have in common. The GCF for this case is also going to be 2x. They can each be divided by 2. They each have an x. So 16 divided by 2 is 8. And we're going to get x squared because x to the third divided by x. 8 divided by 2 is 4. X squared divided by x is x. Now, 2 divided by 2 is 1. X divided by x is also 1. So remember, 2x divided by 2x doesn't just go into oblivion. It still needs to be represented by a 1 there. Okay, now I have 2 letters in common for this case in number 3. So I see that A is present in both. B is also present in both, but notice b to the third and b squared are here. So I can divide them both by a b squared. If I kind of go back for a second, let's say I didn't notice that. Let's say I do this, I get a and b squared minus a will be gone, but I'll still have a b. So I still have a GCF in common there. So I'm going to go back. That's not fully factored if the letters are still present in both terms there. So we're going to change that to b squared. So ab squared is going to be a b minus 1. Okay, last one. In this case, what we want to notice is that the GCF is different. We're looking for what they both have in common. Now I could try to distribute and go through it, but the big thing you want to recognize is that x to the fifth is in both of those. X to the fifth is present for both. My GCF is going to be x plus 5. So I'm going to put that piece out in front. And then what happens is I'm going to put everything from the first term, x minus 1. Then I'm going to bring down the plus and bring everything from the second term, 2x minus 3. And we're going to rewrite this. That x plus 5 is still going to stay intact over here. But we're going to get 3x minus 4 when we combine like terms. And that's what it's going to look like factored in this case. So watch out for those GCFs where you have a binomial sneaking in there. Okay, moving on to multiplying conjugates. I've been teasing that word a little bit as we went through the year so far. But if I multiply these through, we get a squared. We get a negative ab. We get a positive ba or ab, either order, commutative multiplication, right? And then we end up with a negative b squared. Well, we know what's going to happen to that top piece because if you look at the middle terms, they're going to cancel. We get a squared minus b squared. If we end up with something like that, it's always going to be the case. We've seen it. We've hinted at it a little bit so far, but this is what dots is. So if you can get the product of two binomials and it cancels out that middle term, difference of two perfect squares, that is what we refer to as dots. Difference of two squares. We skip the p, but it gets the job done. So basically, if I look, conjugate pairs should be the same, a and b on both. It's only different by a plus or a minus sign. So when I set this up, x times x is what's going to get me x squared. 7 times 7 gets me 49. To get a negative 49, we're going to have plus and minus. Conjugate pairs, they have the same exact look, only the sign in between changes. Same idea in 6, only they reverse the order. So now I have 5 times 5 gets me 25. And y times y gets me y squared. I can switch it to minus and plus. It doesn't matter if the minus comes first, the plus comes first, as long as there's one of each. Okay, now in this case for 7, 9x squared minus 4, 9, we think 3 times 3 gets me 9. X squared we know is going to be x times x. We're ready to do a plus and a minus, and then 2 and 2 for that 4. And finally, we've got x squared, and x squared that's going to get me to the 4th power. We've got a positive 4 and a negative 4. Technically, what you can notice here is this one's not fully done. I've set myself up with x squared minus 4, which can be x plus 2 and x minus 2. But now with the plus sign, pluses are not factorable, Difference here means subtraction. So this is not factorable. Make sure you understand that if there's a plus sign, it's not going to factor any further. So no good for us in that case. All right, our last type of factoring that we're bringing back today is trinomial. Some of you might remember this as the AM method. That means you add to the middle term and you multiply to that term on the end. So I'm going to think about all the factors that multiply to 21. So I know I have 1 and 21. Nothing I know multiplies with 2 to get 21 nicely. 3 and 7. 4 no good. 5 no good. 6 no good. Then I'm back at 7. So these are my options. So out of those options, I'm thinking what possibly multiplies to 21 but adds to 10? It's going to be 3 and 7. So when I write that as factors, we know x times x is going to get me that x squared in the beginning again. And I know 3 times 7 gets us that 21. And if we want to add up to 10, 3 plus 7 is what's going to get the job done. Okay, now it's going to switch along the way here. We're going to do the same thing. Now this time we want to add to a negative 7 and multiply to a 10. So we know we have 1 and 10, 2 and 5, 3 doesn't work, 4 doesn't work, and now we're back at 5. We still know we have x times x, which gets me that x squared in the front. I'm going to go with 2 and 7 being the combo that can make this work. And now if I want it to be a negative 7, I'm going to have a negative 2 and a minus 5. If I combine a negative 2 and a negative 5, if I multiply those together, negative times a negative gets me a positive. But negative 2 minus 5 more is that negative 7 that's in there. So we got to be careful with those signs. Those were both minus, while the first one was both plus. Okay, we're going to do it again. 1 and 15, 2 doesn't work, 3 and 5, 4 doesn't work, and we're back at 5. Again, x times x gets me that x squared. The only combo that makes sense here is going to be a 3 and a 5. Now here we went into a dilemma. technically this was a negative 15. I didn't feel like writing out all the negative and positive versions of what each number could be. I just think, okay, what combination of 3 and 5 can get me a positive 2? Well, if this number is positive, if this adding number is positive, that means the bigger number has to be positive as well. That's true every time, right? The bigger number was positive like it was here. The bigger number was negative like it was here. So we know that. And now I'm thinking if I have positive 5, the way I'm going to get to a positive 2 is if we minus that 3. And I could always double check. I could always distribute through and multiply to see, but that's going to be our answer in that case. All right, keeping it going. 16. 16, we have the factors 1 and 16. We've got 2 and 8. 3 doesn't work. 4 and 4. Once I know I have 4 and 4, I can't go any further. 5, 6, 7. It's not going to work. Anything in between. So x times x gets me x squared. Now, I'm trying to end up with a negative 6. So again, I know this is a negative. I see it there. I know I'm going to have one of each sign. Anytime I see a negative here, I have one of each like I did in this case. So I know it's going to be a plus and a minus to make that work, because if I need to multiply to a negative number, just like on the top, it had to be plus plus because it had to multiply to a positive, negative negative because it had to multiply to a positive. But now we need one of each. So just like before, this piece here is a negative, so the bigger number should go with the negative. So the negative 8 is going to be here. Negative 8 plus 2 will get me that negative 6. Okay, last two of recapping here. So we have 20. We have 1 and 20. We have 2 and 10. 3 doesn't divide nicely. 4 and 5. And we're good. We've stalemated. Now it's different. X to the fourth. So x times x is not x to the fourth, but x squared times x squared goes to the fourth power. So that's going to check out for me. I think about what multiplies there. I'm going to use that. I'm still going to do the same thing. I want to find what adds up to a negative 12. I found the factors of what multiplied to 20. Now I see a plus sign here, which means that they should be the same sign. So I'm going to think we're going to use 10 and 2. 10 and 2 is the most likely to add up to or subtract to a 12, but it's a negative 12. So while it's this 2 and 10 here, it's got to be negative, negative. That negative times a negative makes a positive, but negative 2 minus 10 more gets me the negative 12 that I want. Now, last one, we've got a little bit of situation here. What I want you to do is ignore this y for a second. So x squared plus 5x plus 6. Let's just try to factor that first, and then we'll come back and deal with the y in a moment. So I have 6 that I'm multiplying to. So we know my options are 1 and 6 or 2 and 3. We're still doing the AM method, so we found the multiples, or things that multiplied to 6. And we're going to factor this. We have x and x, business as usual. Now, if I want to multiply to a positive 6 and add up to a positive 5, this is like a hard one because both things have to be positive. Everything should be positive in here. So if I have 6 plus 1, I'm going to end up with 7. That's not what I want as a middle term. So I need to use 2 and 3 because I know if I did 6 minus 1, it would work, but there was no minus sign to be had. Right? If this term is here, that means both signs are going to match because either negative times a negative is a positive or a positive times a positive is a positive. So we set that up for ourselves. Now, the thing to remember is that we kind of cheated the system a little bit up here. We just decided to get rid of a y. Let's think what makes sense. X squared goes in the front too because I had x squared in the front here. And then x was still in the middle. Y squared's at the other end. So instead, when I write this as a final answer, I have x plus 2, I have x plus 3, But on each tail here, I'm going to have a y. Because at the end, I had a y squared. So 2y times 3y is going to get me a positive 6y squared, right? That y comes into play along here to help us. So we just got to be careful with questions that look like that. And we could always distribute to double check. All right, what I want you to do here is pause the video and try to factor each of these completely. So the idea before you pause is that you might need to factor more than once. Like I'd always start by trying to do GCF. GCF is the first one we talked about. It's the first in the lineup. So we check, is there GCF? And in 15 there is 2. So I'd be left with x to the 4th minus 16. Now it said to factor completely. So the second in the lineup that I can check is dots, which does work out here, right? I can do this by dots. I make 2 sets of parentheses. I get x squared minus 4. I get x squared plus 4. And then I still have that 2 floating out in front. But I technically haven't factored it completely yet because I can do dots around 2. So this one can get to be x minus 2 and x plus 2. However, remember, plus signs are not factorable, so I bring down that x squared plus 4, and I still have that 2 floating out from the beginning, so I have 2. So this would be my whole answer. And yes, you do have to write it all together. Factors should be next to each other without spaces in between, without gaps from like one level to the next. Like there should be no gap. There is no GCF in the second one. There's no GCF. We try it, it doesn't work. It's definitely not dots because dots is difference of 2 perfect squares. This is 3 terms, so this is like the one we did before. If it helps you, like I did before, take a minute and just write it as x squared minus 2x minus 35. And then we factor that. We think what multiplies to 35 but adds up to a negative 2. So if this, we have one of each sign, we know the bigger number is going to get the negative. I'm going to say negative 7 and positive 5. Okay, I know that because if I put 35 down the side, I can do 1 and 35. 2 doesn't work, 3 doesn't work, 4 doesn't work. But 5 and 7 works. And then the only thing left to check is 6, which is not divisible. Okay. Like I said, pause the video here for these next 4, and then we'll talk about them in a second. Okay, let's see where we left off. So with 17, you can definitely get a GCF out of that first. So we pull out a 2. Then we're left with x squared minus 2x minus 15 when we divide each piece by 2. We've got the trinomial method. Dots does not work because we have more than 2 terms. So we try this. We add to a negative 2 but multiply to a negative 15. We know we have one of each sign because of that negative with the multiplication. The 2 numbers that multiply to a negative 15 but can combine to a negative 2 are going to be negative 5 and 3. 18, you're looking at dots. There's some extra pieces with it, but it's still just regular dots. You've got no GCF, right? X and Y are not the same. 25 and 49 do not have anything in common. But we can do dots where we take 25 is a perfect square for 5. X squared becomes x, so that term is in both. When I look at it, when I'm going back here, 5x and 5x, we did our minus and our plus because that attached to this piece, so we do plus and minus, and then we have 49, and which got me the 7y and the both the negative and the positive 7y. 19, you're just doing regular trinomial with the AM, but in this case, what multiplies to 12 is either 1 and 12, 2 and 6, and 3 and 4. The only one that will combine back to a negative 1, because remember there's a negative 1 hiding in front of that x squared over here. So negative 4 plus 3 is negative 1. However, because of that x to the 4th, we put x squared and x squared, which meant we could factor a little bit further. That x squared minus 4 can become x minus 2 and x plus 2. And then don't forget to bring the x squared plus 3 down. Last one. We can't do dots here, but what we can do is we can just kind of think of it as this whole thing is being squared. If you want, I can use this little technique where I let u equal x minus y for a second. So I'm going to rewrite this as u squared minus 9, because if it looked like that, we wouldn't think twice, right? I would go, okay, u minus 3 and u plus 3. Now remember, I can bring this piece back in. So I get x minus y. I'm going to have x minus y, but I'm going to be looking at minus 3 plus 3. So that's what our final answer would look like there. You don't have to use that u method, but that whole thing is being squared. So we just bring that x minus y. If that whole thing's being squared, we just bring it before it was actually squared. Then minus and plus, the square root of 9 is 3. All right, guys. Thanks for watching this video. We'll practice more factoring in class together when the next time we see each other. Okay, thanks.